this presentation, so I'm going to stop sharing. And Joan, it's you. You can share. And
Thank you, Krishna. Can you see my presentation?
yeah, you can see it.
Excellent. All right. Okay, thank you, Krishna, so much for the introduction. And in fact, thank you for organizing this webinar series. It's been great. I've learned a lot, to be honest. So I will be on Fridays joining these webinars, and it's been quite a nice experience. Before I start, well, I hope everyone in the audience is healthy and well. Here in Colombia, the vaccine rollout started not long ago. However, it's moving. It's a little bit slow, but it's going on. And hopefully this will improve our quality of life, hopefully this year or next year. And it's always great to be back at UIC, at least, in this virtual fashion. So thank you for inviting me. Before I start, I just want to acknowledge and thank my co-authors. I'm sure you all know Professor Jeff Evans from Cornell. He probably needs no introduction. He's an expert on geoenvironmental barriers and also on engineering education. He's a professor emeritus now at Cornell. Also, Norte Yeboah. Norte is currently a senior engineer at Southern Company in Atlanta. We overlapped during our PhD studies at Georgia Tech. In fact, he was my office mate for maybe 2 or 3 years. He's a dear friend and excellent colleague. And I'm an associate professor at Javeriana University here in Bogota, Colombia. The contents of this presentation are related to a study and a paper that we recently published in Environmental Geotechnics. You have here the citation in case you're interested in reading. And most of the original idea, of course, was from Jeff. And Norte and I performed both the experimental and some analytical procedures. So before I start, I just want to take a few seconds to talk about my university, the institution where I work. Javeriana University is one of the oldest institutions in the country. It was established in 1623 and reestablished later in 1930. We have 2 campuses. The main campus here in the city of Bogota, the large campus, as far as I call it the main campus because of size. But we have a satellite campus in the city of Cali in Western Colombia. Together, between the 2 campuses, we have in the order of 27,000 undergraduate students and 5,000 graduate students. They are in 22 schools, and we have 63 academic departments and 15 institutes. Javeriana is a university of the Society of Jesus, which has universities all over the world. As far as the civil engineering department, our department was established in 1950. Currently, we have the order of 650 undergraduate students and 130 master's students. Most of our research relies on master's students, to be honest, but we have a small doctoral program in the order of 25 doctoral students in civil engineering. Me and my colleagues are 26 full-time faculty, but we also rely a lot on adjunct faculty. We have 135 currently. And the reason is that our class sizes are rather small, in the order of 20 to 25 students on average, and we have 16 administrative staff. Since about 4 years ago, we've been ABET accredited, and the photo you're looking at on the left is our new engineering laboratories building, which was opened to the community in early 2020, last year. So today we're going to talk about vertical barriers. And of course, I'm sure you're all familiar with the concept of vertical barriers. Basically, they are engineering structures that we use to either contain or even treat contaminants within the soil. So what you're looking in this schematic on the left-hand side is a contaminant plume, probably from an industrial source. And this contaminant barrier is a vertical structure that tries to encapsulate the contaminant or in some cases to treat the contaminant via what we call reactive barriers. On the right-hand side, what you're looking at is a schematic of a cutoff for the reclamation in the perimeter of an existing landfill from these publications that you're looking at here. And basically these cutoff have the purpose I just mentioned, either encapsulate or treat the contaminants and the contaminant plumes. Out of the many vertical barriers, you're seeing a list of, the most common ones or the most studied ones. Some of them are self-hardening, some of them are not. So basically, we have soil bentonite backfill vertical barriers or slurry trench cutoff walls, which are the most widely used in the US, for example. But we also have soil cement bentonite backfill barriers, cement bentonite slurry walls, slag-cement-bentonite, or what I call slag-CD, slurry trench cutoff walls, fly ash cement bentonite slurries, high density polyethylene geomembrane, so that's in the field of the geosynthetics, plastic concrete, curtain grouting, and so on. So for today's presentation, I'm going to focus mostly on slag-CD, slurry trench cutoff walls. So as far as the history or development of these systems, particularly slurry trench cutoff walls, what you're looking at is a timeline where we can see that back in the 1940s, last century, maybe the first half of the 1940s, the first field tests were performed in the USA and Europe for these type of systems, but not only until the late 1940s were the first cutoff walls constructed and placed in operation in Italy and the US. Later, maybe 10 years later, in Europe, this slurry trench technique was successfully applied for structural element installation, and that has been done from that point forward up to this day. And in fact, in 1968 or so, the original World Trade Center slurry wall in New York City was completed using specifically these slurry trench cutoff wall or slurry trench technique rather. It is not a slurry wall, but a concrete wall that was constructed using the slurry wall technique. And it contains the waters from the Hudson River into the excavation of the World Trade Center. So then in the 1970s and 80s, the use of these systems was expanded for environmental containment. And from the 1990s towards this day, it's a widely accepted system or technique for geoenvironmental cutoffs and also structural elements. Now, if we take the US and the United Kingdom as perhaps a benchmark or a framework for comparison, what you're looking at in this table is a comparison of the practices and outcomes in both places. So in the US, the most widely used slurry trench cutoff wall is the soil bentonite one, SB. However, in the UK, by far, the most widely used is slag-CB cutoffs. The construction stages are different. There are two phases in the US practice and one phase in slag-CB walls, but the excavation equipment is pretty much the same, backhoe and clamshell. The depths are also similar, less than 20 meters, typically for these types of walls, but the width is a little bit higher or larger in the US or in soil bentonite rather, about 75 centimeters, whereas in slag-CB is typically 60 centimeters. Also, perhaps a major difference is that typically the lengths of these walls are longer in soil bentonite systems, more than 1 kilometer, than they are in slag-CB systems. And another major difference as far as logistics of construction is that the working space required for the implementation of the systems is typically larger for soil bentonite slurry trench cutoffs because they use slurry plant backfill mixing, whereas for slag-CB system is rather modest because they use slurry plant excavation and spoil disposal. So in both cases, though, the bentonite is typically sodium monovalent expansive soil. What you're looking at here for soil bentonite cutoffs is the typical, or a schematic rather, of the typical construction process of these type of systems. So you have here an excavated backhoe that is digging the trench up to a certain depth. At the same time, a slurry prepared with bentonite and water, typically 5% or so bentonite, is prepared and is filling the trench to avoid collapse of the trench and the excavation itself. And it's permitted to settle for some time. In the meantime, mixing bulldozer is basically dumping in a controlled fashion the soil bentonite backfill in this fashion, like a diagonal fashion, like you can see here, until the whole trench is filled, and of course, there is a quality control process in the middle, and the soil bentonite cutoff can start operating. As far as slag-cement-bentonite slurry trench construction for cutoffs, what you're looking at are some photos courtesy of Jeff Evans, and these photos are from the late 90s in the UK, in the United Kingdom. This is an excavation through the top of a dam at that place, and that's where you see the process of digging the excavation and allowing the slurry to prevent collapse and to set in the initial stages of construction. And what you see here on the left-hand side is a close-up of the hardened slag CB material at the top of the wall. And you can see a deep blue coloration due to the manganese in that slag. On the right-hand side, what you see is a slurry plant or slurry mixing plant, which is rather small in size for this type of construction. The silos that you see here are where bentonite, slag, and Portland cement are stored. And the bentonite water slurry is made at this plant, and then cementitious materials are added. Finally, what you see here on these photos on the top are the process of sampling a cured slag CB core of wall. They are taking samples from an existing wall at a contaminated site with coal tar at the UK. And actually the photo on the bottom is also a sampling process from a 10-year-old slag CB cutoff. So as far as properties of slag CB, which is the main topic of this presentation, what you're looking at is hydraulic conductivity against time. And these are data, and actually you can find a large body of evidence in the literature regarding hydraulic conductivity properties evolving with time of these types of materials. So what you're looking at here is 4 curves with different slag replacements, granulated ground blast furnace slag, is, of course, as you know, replacement cementitious material in these mixes. And normally the replacement percentage is in the order of 80%. And as you know, slag is a byproduct of the iron production industry. So in a way, we are, reusing waste material in these type of processes because slag has cementitious properties itself. So for design, typically the hydraulic conductivity of slag CB cutoffs is in the order of 10 to the minus 9 meter per second or less, which is basically the straight horizontal line or dashed line that you are seeing here in this plot. Now, there are a couple of numbers that I want you to keep in mind during this presentation that normally are very important for these type of mixes, but we do not really quantify or account for them all the time in practice. First of all, the water to cement ratio. You may recall from materials or structural engineering that concrete and mortar are materials with rather low water to cement ratios. Concrete maybe in the order of 0.5 or so. Mortar, a wider range, but also not too far from the low range values. However, when we quantify that water to cementitious material, that is including the Portland cement and the slag, for slag CB mixtures, we have a much higher number, an order of magnitude higher number because of the proportions that are normally used during field construction. So it's in the order of 6 or 6.3 water to cement or water to cementitious ratio. Now, the second number I want you to look at is the ratio of cementitious mass, that is either Portland cement or Portland and slag, divided by the dry soil mass, that is bentonite. And these numbers are very important because there is a lot of evidence, a lot of studies and research evidence from the field of expansive soil stabilization, swelling soil stabilization, for example, with lime or with cement, slag, or slag cement. And these numbers are in the order of 4 to 20% overall for this type of expansive soil stabilization. And I'm going to be talking about these types of methods to support the discussion of my research. So if we compare that with what happens in slag-CV mixtures, we have also very large numbers in slag-CV mixtures in the order of 2.5, also roughly one order of magnitude higher. So I wanted to keep these two numbers in mind for the remainder of the discussion because they are going to help us understand the data that I'm going to present later. So as far as background, we also need to remind or to understand a little bit of cement chemistry and cement hydration processes because these processes are very active in a slag-CV system, but they are not normally studied, or at least they are not frequently looked at during design or operational processes. So what you're looking at here is the typical reaction that takes place when cement gets hydrated with water and what are the main byproducts or products that are produced. So cement has a major chemical phase, which is called tricalcium silicate. And by the way, in these reactions, I'm not presenting the typical element or stoichiometry with the chemical elements per se, but I'm using cement chemistry notation. So I'm using the language that cement chemists use, which is just like with shorter terms for each one. So this C is not carbon, by the way. This C means calcium oxide. S is silicon oxide, and H is water for this notation, and that's the way cement chemists talk. So tricalcium silicate is the major phase in Portland cement, is this formula here. And when it reacts with water, it basically produces two major products. The first one is calcium silicate hydrate, CSH, and I'm going to be talking about that later on. CSH is a major strength contributor to hardened cement, and in fact, hardened concrete as well. And it is one of the major important phases that is produced. But equally important, we have also calcium hydroxide. And as you know, calcium hydroxide delivers very alkaline conditions, very high pHs, and also this reaction overall is exothermic. So in summary, the hydration of cement delivers pretty aggressive conditions in the environment where it takes place. A second reaction I want to look at is carbonation. When we have the abundance of calcium from the dissolution of calcium hydroxide and CaH, which, like I say, takes place during cement hydration, when this calcium combines with atmospheric CO2, we know this reaction and it delivers calcium carbonate, the mineral calcium carbonate. So this is well known in the cement chemistry literature. And the interesting thing is that in CV slurry systems, or even in slag-CV slurry systems, which are being constructed at a certain depth, say 15 meters below ground surface, there is probably another source of carbonate, which is bicarbonate ions dissolved in groundwater. So these processes are, in a way, plausible in a slag-CV cutoff. And finally, I just wanted to mention puzzolanic reactions. I'm sure you are familiar with them as well. You may remember that when calcium hydroxide combines with a puzzolanic material, which is typically from volcanic origin or calcination, for example, metakaolin, even fly ash has puzzolanic properties. Some fly ashes have puzzolanic properties. Those are materials that are high in silica, but typically low in calcium. They are going to produce at ambient temperature a calcium silicate hydrate. And this material has cementing properties. And that's why puzzolanic materials are interesting and useful, because from a material that does not have cementing properties, with reaction with calcium hydroxide, you get a material with cementing properties. Now, if the puzzolanic material is high in alumina as well, you also typically get calcium aluminate hydrates, both of them at ambient temperatures. What is interesting is that the field or the study of puzzolanic reactions is a very widely known and well-studied field in lime stabilization or even cement stabilization of swelling soils. However, these principles have not been very well or deeply studied for the field of contaminant barriers. So that's where we are looking at right now in this present study. I just want to mention that if certain phases like sulfates, carbonates, or chlorides are present, these same reactions may produce a tringite. And this mineral, tringite, is a complicated mineral for engineering applications because it also has swelling properties as well. Now, as final background, it turns out that back in the 1960s, Jim Mitchell and other collaborators, and also many other researchers, have looked at mineralogy of, let's say, mixtures of, or not rather mixtures, but stabilization of clay soils or swelling soils with either cement or lime or other cementitious materials. And what you're looking at here are the X-ray diffraction patterns of montmorillonite with 30% cement. The top pattern is after 1 day of curing, and the second or the bottom pattern is after 3 months of curing. And what I want you to look at is that there is a very significant decrease in this particular peak, in this particular band of the X-ray diffraction patterns, which is precisely the band that signifies montmorillonite, the band that represents montmorillonite in a random powder mount X-ray diffraction pattern. So what this is telling us or suggesting us is that there is a significant mineralogical change and mineral change within structure of the montmorillonite mineral during the 3-month curing period. So I want you to keep in mind that also for the discussion that is coming up. And as far as properties, and to close this background, of course, shear strength and permeability are affected by the slag content. This granulated ground blast furnace slag is used as a replacement or partial replacement cementitious material in very large proportions, typically from 60 to 80% replacement within the cementitious component in slag-CB mixture. So you can see here that there are typically important changes and increases in strength, or at least accelerated strength, if you will, and also significant changes in hydraulic conductivity due to the presence of an important amount of slag within the cementing component of the mixture. All right, so putting all this in perspective, we decided to cast a research question, and is, if we have a slag cement slurry wall and the mixture in proportions for field construction, what is the evolution and what is the importance of all these concepts in slag-CB systems? And in particular, we were interested in what was the fate of the bentonite. Is the bentonite really contributing in the long term to, say, hydraulic conductivity and perhaps other properties related to contaminant encapsulation? So this is basically our driving question for this research. So what originally Norte and Jeff did back in the lab was preparing two mixtures, two main mixtures of slag-CB, and then they applied mineralogical methods to try to study the evolution of those mixtures over time. So what you see here on this taller column here is the mixtures that are representative of field construction in typical slag-CB cutoff projects. What you see on the right-hand side, though, is a second mixture that was prepared for validation, or for, if you want, sort of confirmation of the previous one, and it's a spiked mixture. It's a high bentonite content mixture, and you can see the proportions over here. So for the field representative mixture, again, this is typical of slag-CB wall construction. The slurry has a 6% bentonite content. And like I said before, the amount of slag replacement within the cementitious components is in the order of 80%. Of course, 20% Portland cement. You can compare side by side also with the high bentonite mixture. The composition per total mass is just 5% bentonite, because most of it is water, of course, and 13% the overall cementitious components. However, if we look at those same numbers per dry mass, that is per dry mass of total composition, the bentonite is 29%, and the cementitious material is significantly higher, 71%. That, in fact, is reflected on the three numbers at the bottom, which I showed before. In fact, the ratio of total cementitious mass to dry bentonite mass is in the order of 2.5, whereas in that 2.5 number is composed of 0.5 Portland cement and 2 slag. Okay, and like I said, side by side, you can compare with the second mixture that was studied for this particular study. So with these mixtures, we started experimental program. First, we prepared, or we kind of simulated in the lab the process of slurry preparation. And you have here bentonite water slurry mixture, which was basically mixed in a blender. And after overnight, or say 24-hour setting of the slurry, the material was mixed with cement and slag. And after that, it was transferred into a number of molds, like you can see here, plastic molds, which were cured at 100% relative humidity for a certain period of time of up to 3 months. And after, with some frequency within that time frame, we were testing for scanning electron microscope images and X-ray diffraction patterns in random mount fashion. So results, what you're looking at here is on the left, well, actually in both photos, what you can see when you basically get bentonite from a commercial provider. What you don't see are individual particles. What you typically see are aggregations of bentonite, or rather sodium bentonite, montmorillonite clay particles in what we call here clumps. So these aggregations, like you can see on the right-hand side figure, are more silt size. You can see the scale bar here of 20 micron across, and basically you cannot see the individual particles of montmorillonite. They are aggregated in this fashion. Another thing that is very interesting to see in these photos is the relative size of bentonite clumps to cement particles. And what you can see here is that the Portland cement particles are actually silt size as well, and they are much larger typically than individual clay particles, and of course even larger than the bentonite aggregations. So this, we believe, is going to have implications in the chemical reactions that take place when this gets hydrated, because being the cement particles larger than the bentonite and clay particle units, probably the reactions are going to be heterogeneous. That doesn't mean that the reactions do not take place. Of course, they take place, but they are not necessarily like very fine powders combining and hydrating with one another. So this is important information to keep in mind. So as far as X-ray diffraction patterns, what you're looking at here is the typical representation of X-ray diffraction data. On the x-axis, you have diffraction angle in 2 theta fashion, and on the y-axis, you have intensity in arbitrary units for the discussion. And you can see here 3 patterns, one for the individual raw bentonite, just as received from the commercial provider, Portland cement, and slag, the replacement cementitious material. So what I want you to look at is the main peaks that allow us identification of the main minerals present here. So for the bentonite, we confirmed, of course, that it was a monovalent sodium montmorillonite, and that has to do with this main peak that you can get from random powder X-ray diffraction testing. It's in the order of 12 angstrom or so, the D spacing I'm talking. And that gives us positive identification of the bentonite. Also, in Portland cement, as expected, we found tricalcium silicate, which also has different names depending on the source you look at, and particularly whether or not it's a natural or manufactured product. And finally, the slag. The slag, for the most part, is amorphous, and that can be evidenced here with this white hump in the X-ray diffraction signal. And that has to do with a lot of glass being present in this material. However, we also found, and you can see here, some peaks that are representative of other materials that have been reported in the literature as well in slags. Uh, um, Calcium sulfate, melilite, and coesite, some particular minerals that are present typically in slag materials. Now, what you're looking at now are the results of the field representative slag-cement-bentonite mixture that we tested. So what you see here are 5 stacked patterns, one for each time or moment in time within a framework or a window of 3 months. So we have data for 0 days, that is pre-hydration. And then we have data for 1 day, 3 day, 18 day, and 91 day hydration period, and curing under 100% relative humidity conditions. So of course there is a lot of data here, and I'm gonna break it down for you in just a second. For now, what I want you to look at first is the U peak. I labeled it U for the lack of other letter to use here. That is an artifact of the testing, which is aluminum, because the sample holders that held the actual samples were made of this metal. So this peak is widely, of course, it's very sharp and very high, but it's not significant for this study. And second, the Q peak, which is quartz. Interestingly, in real field applications, when the slurry wall is being constructed, a lot of sand or perhaps other soils gets into the mixture and gets into the trench, actually, just as a contamination, if you will, as a cross-contamination material or soil from the construction process. However, for this particular study, we did not intentionally add sand or other soil just to prevent misinterpretation of the data. However, you still can see a very tiny little peak of quartz here that is going to be remaining in most of the X-ray diffraction patterns. Second, and again, there's a lot of data here. I'm going to break it down for you in a moment. This is the stack pattern of high bentonite content mixture. So this is the spiked mixture that with high bentonite content, and I apologize for that noise. You can see here again the aluminum holder signal and the quartz signal as well. So, as promised, I'm gonna explain the data like separately just to identify the different minerals that we found. So, first of all, in both mixtures, in the field representative and the spiked mixture, we found, of course, sodium monometalite in the very first state, in the dry state at 0 days. However, we confirmed the findings of Mitchell and many other researchers later. You can see here that during the first days, pretty rapid during the hydration process with slag and cement, the peak of bentonite is no longer a peak. It becomes a hump. And in fact, it tends to shift a little bit to the left-hand side. So what we confirm here is clay mineral destructuring that has to do, we believe, with dissolution in the aggressive environment promoted by calcium hydroxide and exothermic environment during cement hydration mainly. So what you can see here also is that beyond perhaps the 18th day, you can argue that you no longer have really monometalite. The slight shift in the peak may have to do, or actually we believe it has to do with cation exchange that is taking place because at that pH, the particular calcium oxide or calcium hydroxide form tends to replace or transiently replace the sodium by the calcium in this structure. These findings were also confirmed in the high bentonite content sample. So you can see here again, the peak, and again, the fading of the peak as the time moves forward towards 3 months, basically. So to us, the key points to take here from this first point of bentonite dissolution and perhaps the implications that it also has is that the very high ratio of cementitious mass to bentonite mass that I mentioned earlier, about 2.5 for slag CB systems, that is typical for these mixes, promotes rapid bentonite dissolution. And that again has to do with a very chemically aggressive environment that takes place there. Second, while bentonite plays a key role in maintaining the low hydraulic conductivity in an soil bentonite wall, like I said, that's the main practice in the US, for example. In slag CV walls, or even CV walls probably, the role of bentonite is largely short-term. You can see that within the matter of days, the bentonite structure basically fades away. And third, in the long run, we believe that the slurry wall's hydraulic conductivity is a result rather of the hydrated cementitious structure. That is the cement hydration products and other products that I'm showing in just a second, not the bentonite, because the bentonite disappears rapidly with time. Now, if we look at the same patterns that we saw before, but with a different mineral in mind, that is calcite, calcium carbonate specifically, we confirmed the presence in the enhancement of calcite over time. So you can see here clearly that from 0 days up to 3 months, basically you get sharper and very distinct calcite peaks. This happened not only in the field representative sample, but also in the spiked high bentonite sample. So what we confirm here is carbonation. We believe carbonation is taking place because in this case, CO2 from the atmosphere is being absorbed, let's say, by the mixture, and the calcium specifically reacts with it in order to produce calcite. And in fact, no other calcium carbonate polymorphs were found in this particular study, only calcite. The same data, we can plot it in this chart, and what you see here on the x-axis is the number of days, up to 3 months roughly, since hydration, and in the y-axis you see a relative height of the main peak from the X-ray diffraction patterns when we compare calcite divided by quartz, because quartz was basically constant during the testing. So what you see here, except for this small decreasing trend that we, to be honest, we haven't explained that, we see a general trend of increasing calcite, let's say, intensity of the peak. That intensity of the peak typically reflects either crystallinity or content. So we believe, anyway, that carbonation is taking place. So to us, the main key points and implications of this is that due to the formation and enhancement of calcite, the barrier effectiveness may be compromised if the target contaminant is acidic in nature. We all know that calcite is vulnerable to low pH conditions, to acidic conditions. So for example, if this slag CV wall is intended to encapsulate a contaminant plume from an acid mine source, we may have problems with calcite performance, or rather wall performance in the long run. Also, we believe carbonation may be hindered under field conditions. However, this is something we are starting to explore, and I'm advising a new PhD student who is intending to look into these processes. And the problem is that we believe that atmospheric CO2 may be scarcely available under real construction conditions. However, we have some data or some evidence that indicates that bicarbonate ions may be a good enough source for the development of calcite. Finally, something that we were not being able to find in the literature for contaminant barrier systems, but we have found extensively for swelling soil stabilization research, is the formation of puzzolanic minerals. So these are the same patterns we've looked at in the last few minutes, but I'm highlighting 3 puzzolanic minerals that we positively identified in this study. The S label here is consistent with calcium silicate hydrate, again, CaSH. However, this particular peak over here, which if I recall well, is 1.8 angstrom or so in this spacing, is a particular puzzolanic form of this CaSH mineral that we often find in hydration of cement. Second, the X label indicates quaternary hydrated aluminate, which is a well-known puzzolanic mineral formed in some systems of lime stabilization of swelling soils. And what was surprising for us was to find almandine. Almandine is not expected, it actually has not been reported previously as a puzzolanic reaction product. However, we confirmed it. This is an iron aluminum silicate. And of course, there is let's say, a new field of research here in order to see whether this mineral has, for example, sorption properties of interest. For the spike sample, for the high bentonite content sample, what is interesting is that we did confirm the presence of new puzzolanic minerals, and you can see the evolution of them with time. There are very sharp peaks at 3 months, and perhaps there are sharper peaks if this study had been performed in a longer period. However, the minerals that we confirm are different. They are distinct from those in the field representative sample. We have, I hope to pronounce this well, herenbergite and potassium dioxide, both of them calcium iron silicate. And those are puzzolanic products, and they have been reported in the past as puzzolanic products as well. So what we believe are the main implications and key points to take home from this is that bentonite clay minerals, and this is probably the most important statement of this presentation, to us, bentonite clay minerals may actually be thought of as puzzolanic precursors required to enhance cement hydrate formations. And these may have implications, and I'm saying may because this is basically a new field of study, and hopefully new research will be done in this area in the coming years. These hydrates, the puzzolanic hydrates, are known to improve some of, or may possibly improve some of the barriers, contaminant sorption properties, which, like I said before, can no longer be attributed to the bentonite because the bentonite disappears quickly due to the reasons I explained before. So what we do know, though, is that the field of lime or cement stabilization of swelling soils has told us that the sorption capacity of a clay cement or slag clay cement material depends on the sorption capacity of the cement hydrates. And those are the hydrates I'm talking about when I mention puzzolanic products. These materials or minerals provide strong sorption sites for many contaminants. And this is a widely unexplored field of research that we are looking forward to tackle in the next few years. So overall, the implications of all this is that to us, the well-known mechanisms of bentonite volume change in response to changes in pore fluid chemistry, and you all know the diffuse double layer theory, the Deville-Huckel double layer thickness, and so on, are excellent approaches for soil bentonite systems. However, they are not applicable for slag CV systems because the bentonite fades quickly over time. And having said that, we learned that while the fate of bentonite is in the puzzolanic minerals form, however, bentonite, of course, is a critical ingredient. It's an instrumental variable required for slurry workability during slag CV construction, and it should be continued to use in the upcoming decades. Also, browsing the literature on these topics, we found and we learned that definitely there is an overemphasis in previous studies on the role of hydraulic conductivity, which is, of course, a critical parameter. However, for actual vertical barrier performance is not the only parameter that takes place. Little research, in fact, has been performed on diffusion, sorption, reactive transport properties, and so on. Perhaps reactive transport has been studied more in reactive barriers, but not in encapsulation barriers. And what you're looking at here at the bottom are one of the few studies that we could find from Fratalocci and others in Italy, as far as breakthrough curves, sorption properties, and so on, of cement bentonite mixtures prepared with slag cement. And of course, with this data, you can calculate or estimate diffusion coefficients and sorption parameters as well. So in conclusion, to us, the long-term hydraulic effectiveness and performance of a slag CV barrier is not due to the presence of the original bentonite. However, the bentonite, of course, is very important for construction purposes because the bentonite gradually destructures and dissolves over time. Having said that, we believe that the traditionally accepted concepts of compatibility that are normally applicable for soil bentonite barriers are not applicable to slag-CV barriers, or in fact to cement-bentonite barriers, because the bentonite does not exist in a fully hydrated slag-CV wall. To us, a possible implication of the calcite presence is that it may render the barrier vulnerable or susceptible to chemical degradation if the contaminants are acidic. And finally, the cement hydrates derived from hydration and pozzolanic reactions or we believe they may be expected to control the barrier's long-term contaminant transport and sorption properties. And this particular point is underexplored in research. So we hope to start tackling these problems in some time. So thank you so much. I just want to acknowledge my university and the research grant that allowed me to perform some of this research and to visit Bucknell at some time a couple of years ago. Brad Jordan of the geology department at Bucknell University, a very nice person and scientist who helped us with the testing, the XRD testing and interpretation.